So this is the deformation. And the deformation is about the what? The y-axis, or so-called this rotation over here, right? You can see so-called like a rotation. I'll highlight in, okay, like I'll highlight a rotate. It's like a rotation down here. It's rotating about the y-axis. Okay, so we can see that the curvature or the deformation curvature is about the y-axis, right? So for this case, right, the formula that we're going to use, we are going to determine the P critical, right, will be equal to pi squared E, right, and then we have to over L squared. Now the I will be YY. Okay, will be the second moment of area will be about the YY axis. Okay, I repeat again, the second moment of area will be the YY axis. Now, the next way, the next possibility that this structure can buckle is about the XY plane. Okay, so now we look at the XY plane. Okay, so now I'm going to construct the XY plane. So this is my X, and this is my Y, and over here, this is my rotation about Z. Okay. So now if I was to sketch the structure out, okay, so the structure now I'm going to sketch out. And then I'm going to draw the centroid. Oh, I'm sure I've drawn the centroid in just one green line for this case. Okay. Now the deformation pattern for this case will look like this. For buckling, okay. Oh. Okay. So again, this has a radius of curvature about the z-axis. Okay, so we note down here the deformation curvature is about the z-axis. Okay, so for this case, the formula will look like PCR is equal to pi squared over L squared E I Z Z. Okay, so we have two now. We can use IYY or IZZ. Which one to use? We have to determine, or we have to find out by selecting the lower second moment of area. Okay, I repeat again, we have to, okay, so from here we have to determine the lower second moment of area. Why is that? Okay, because if you look at the equation on the left and on the right, pi is constant, E is constant, L is constant. The length is going to be 6 meters. What changes is the second moment about IYY and the second moment of IZZ. Okay, so the next thing we have to do now is to determine the second moment of YY and IZZ. Okay, so I'm going to take this whole graph, okay, and I'm going to teach you how to find or how to determine what is YY, IYY, or IZZ. Some of you will have forget. So I'm going to take this graph. So take this image. Okay, and I'm going to come down here. I'm going to paste the image. Okay, I will take 2. Okay, so copy and paste. And this is important because later on in this course, we are going to do 3D deformation, okay? Or sorry, not 3D deformation, what I'm talking about. We're going to do compound loading. So loading in 3 different axes. You have to know how to determine IYY and IZZ, okay? So let me put in the transformation first. This is Y. And this is Z. And over here, the same. This is Y and this is Z. Okay. So on the left-hand side, we want to determine IYY. And the formula is equal to width, depth, cube over 12 plus by the area, bracket Z, big Z, minus small z, and the whole thing squared. Okay. The big Z means the global centroid. The small z is the local centroid. Okay, the local hold on, the local centroid. Likewise, over here, we are going to do IZZ. So this is equal to width, depth, cube over 12 plus by cross-sectional area, big Y bar minus small Y bar. Okay, and the whole thing squared. So it's the same, the big Y bar or Z bar over here is the global centroid, and the other one is the local. Okay, global means for the entire structure. Local means when you divide them into individual parts. Okay, so now we are now going to find IYY. Okay, so we know IYY is first moment of area about the YY axis. Okay, so you draw your YY axis. Okay, so I'm going to sketch my YY axis. And from here, we know that this is exactly the centroid because the top and bottom half are the same in geometry. So this is our YY axis. If that is the YY axis, the geometry that is parallel to the YY axis is known as the width. The geometry that's perpendicular to the YY axis is always the what? It's always the depth. Okay. So over here, we know that this is our I'm going to call this section 1. This is my section 2, and this one is our section 3. Okay. So I'm going to find IYY1, which is equal to IYY 2, and this is equal to, so we know that the width is 9.5, the depth, which is 40 over 12. Now you don't have this term over here because the global centroid and the local centroid are at the same position. So this term over here is equal to what? 0. So you calculate over here is 9.5. 9.5 times 40 power 3 divided by 12 is equal to 50.667 times 10 to the power 3. And this is in millimeter 4. And then we are going to determine I, Y, Y at number 3 section. So the width is equal to 120. The depth is 9.5 cube over 12. So this will be equal to 120 times 9.5 power 3 divided by 12 is equal to 8.57 4 times 10 to the power 3 millimeter to the power 4. Let me do it again. 8.574. So IYY will be equal to twice of 50.667. Then plus by 8.574 times 10 to the power 3. Okay. So 50.667 power 3 times 2 plus by 8.574 power 3 is equal to 109.109 908 times 10 to the power 3 millimeter 4. Okay, so let me see again. So the width is 9.5, the depth is 40 cube divided by 12, 50 point. So 9.5, 40 power 3 divided by 12 is equal to 50.6%. So the other one is the width is 120. 120 times 9.5 power 3 divided by 12, 8 point. So 50.667 power 3 times 2 plus by is 109.908. Okay, 50.667 power 3 times 2 plus by 8.574 power 3, 109.908. So that is our IYY. Okay. So next we calculate our IZZ. Okay, our IZZ. So again, this is our section 1, this is our section 2, and this is our section 3. So now this is our ZZ now. Okay, so this is our ZZ. So that is the axis of interest. So that's the case. This is the width, and over here, this is our what? Our depth. So IZZ, we know there is a centroid. Okay, so over here, this is our individual centroid. Okay, right? So from here, we know that IZZ 1 is equal to IZZ 2. So this will be equal to the width. The width is equal to, oh, I think I got this wrong. I do apologize. The 40 is per side. Sincerely apologize. So my value is wrong. So this is 80. Do apologize. Okay. I think someone see it. Okay. How did you get 0 from the centroid term? How do I get 0 from the centroid term? Because for on the one that's over here, the ZZ, right? The ZZ, we know that over here, this is the centroid. And then for section 1, if I just draw section 1, right, the centroid is exactly at the same point. So the distance is equal to 0. Lee, does that make sense to you?
Yeah.
Okay. So I got this wrong. So 9.5 times by 80 power 3 divided by 12 is equal. So again, 9.5 times by 80 power 3 divided by 12 is equal to 405. I got this wrong. 405.333 times 10 to the power 3. Let me try again the width. 80 power 3 divided by 12 times 9.5. That's the depth 105 point. The width, the depth 80. Okay, so this is 405. Times 10 to the power 3. 333 power 3 times 2 plus 8.574 power 3. So it's equal to 819.24 times 10 to the power 3 millimeter 4, or 819.24 times 10 to the power of minus 9 meter to the power of 4. Okay, so the first term up here, this is to the power of 3.